So we're going to be talking about Ohm's law. Now, this is probably, if you type in Ohm's law, this is what you get. But actually, Ohm's law is this relationship here, V over I equals R. And I'll explain why in a few seconds. But we're going to talk about this because this is an adaptation of Ohm's law. But first off, I'm actually going to do a bit of explaining about what all these things here. So this is, we've met this before in Q equals IT. This is current. This is a resistance of an object, and this is the potential. And this is what I want to talk about here. Sometimes people will call it the voltage, and they'll be kind of correct, but I'd rather say it's potential. Okay. And I want to talk about this formula here. This formula is not on the specification, but it's useful to understand what this means. Okay. So potential is all to do with energy that electrons have. And what it's actually saying here is that I've got a current going into a resistor, and I'm going to measure the energy that the electrons have here. So I'm going to measure the potential here, and I'm going to measure the potential here. So I'm going to look at the energy the electrons have. So this is energy, and this is charge. So energy equals potential times charge. So I could look at the energy the electrons have going into here, and I could look at the energy that's coming out of here. So this is the voltage going in. This is the voltage going out. Okay. And then I could look at the difference. Okay. So the potential difference is the difference in the potential of what was out minus what was in. Okay. So I'm looking at the difference between here. Okay. And so what a voltmeter does is it looks at the energy of the particles going into this, or the electrons going into the resistor. It looks at the electrons, the energy that the electrons have leaving the resistor. And it's able to go, cool, I know, for example, let's say there's 10 volts here and there's 8 volts here. So looking at the energy, and then they will divide it, the voltmeter will divide it by the charge of an electron. And they'll go, well, there's 10 volts in here, there's 8 volts in here. So I know that 2 volts worth of potential, okay, was lost over that resistor. Okay, so that's why we call this one sort of potential or potential difference. Because when we're measuring it in circuit, it's always that we're looking at the potential before and the potential after. Okay, so let me go into a little bit more what I mean by potential before I go into Ohm's law. That if I had a circuit like this, okay, and the circuit is providing 10 volts of potential, I know that every electron that is going to be moving around my circuit when it goes through that battery is going to be provided with an amount of energy. So I'm going to do 10, okay, equals the energy divided by the charge of an electron. And you will always be given this, but I know this as 1.6 times 10 to the minus 19. So in this case, I've got 10 times by 1.6 times 10 to the minus 19 equals 16 times 10 to the minus 19. I'm being a bit lazy, okay? So every electron that is flowing around this circuit is going to be given this amount of energy, okay? And then if I actually wanted to, what happens to this energy depends on the components it goes through. Now, wires, we assume that when the electrons go through the wires, nothing happens, okay? That there is no transfer of the electron's energy to something else. But when it goes through different components, that energy that electron has, that might be transformed into all sorts of things. So for example, in an LED, that energy might be converted into light energy, or in the terms of a resistor, going into heat energy, or in terms of, I'm thinking of other components, buzzers, it turns into sound energy, etc. So what happens is that the energy that electrons have, they are given it here, they lose it in the circuit, okay, and they come back here and pick up some more again. Okay, so that's what potential is. Potential difference is the measurement of the energy before it goes into something and the energy after, and that difference between it. The reason we prefer using potential instead of energy is, firstly, it means that we're not talking just about electrons. It could be of any charges that are moving. Okay, so by using potential, we're not just talking about electrons. We could talk about circuits with other things flowing in them. But also potential, it has more of a connotation to something called electric fields, which you will kind of touch upon with capacitors. Okay, so what Ohm did is he looked at materials, okay, and these materials were conductors. Okay, they did conduct and allow electrons to go through, but he noticed that different materials, if he was measuring the potential before and after, there was a very different response to different materials. So if I can imagine this here, so this is the inside of a wire or a resistor. Okay, so this is my resistor. The electrons are going through, and what's going to happen is that the electrons have some energy. They might collide with some of the particles in that resistor, which will cause the electron will lose some energy. Okay, so when it will lose, the electron will have less energy. Okay, so less energy here. What will happen is these particles will vibrate more, and of course that would generate some more heat. Okay, but what Ohm noticed is that if he had the same resistor, if he put more electrons through or more current through, he noticed that the amount of energy that was lost also increased. So it makes sense. If I put more electrons through, there's more chance of hitting it. And he worked out, if he actually plotted, he plotted the amount of energy that was lost versus how much current he put through. He noticed that there was this relationship here. And when he changed the material to another one, he noticed that the relationship was the same, but the amounts were different. And Ohm came up with this idea that voltage for resistors, for a type of material called a resisting material, was proportional to the current. And he ended up with V equals I R. And he worked out this property of a material called its resistance. Its ability to basically take energy away from electrons. It resists the flow of currents by slowing it down, taking the energy away. Okay. So if we go back to looking at this graph here, if we look at the graph of V equals IR, if I have a bigger resistance, okay, I would lose more potential. And so on this graph here, this purple line here has a bigger resistance than this one because it has a steeper gradient. So the gradient of this graph, because it is constant, this is what led Ohm to do resistance. Okay. So that's what Ohm did. He put more current through and measured the potential between two bits. And then he noticed that if he changed the material, the actual ratio would change. So let's actually have a go at trying to use this formula. Okay, so let's say I had a current of 5 amps. So this is actually looking, by saying 5 amps, I'm making the whole electron thing much easier to manage, okay? And before they come into the resistor, they had a potential of 8 volts, okay? And when they were less the resistor, they had a potential of 5 volts. What is my resistance? So 5 amps have entered and 5 amps have left, okay? Current does never flows through a voltmeter. It's there. It's like a probe. It's going in to just detect. Okay. So over this, I have lost 3 volts. So my potential I have lost is 3. And the current that went through was 5. So 3 equals 5 times R. 3 divided by 5 is 0.6 ohms. So this resistor must be a rating of 0.6 ohms. Okay. So what happens, you guys can go, I'm going to keep the potential difference the same. So the potential of the current going in here was 8, and when it left it was 5. Okay, so the reading on my voltmeter was 3 volts. Let's say I had 2 amps this time. What is this resistor? So it's taking away, less current's going through, but it's taking away the same amount of potential. What is the resistance on this new resistor that I've put in. Okay, so my potential is 2 and my current is, no, my potential is still 3, but potential difference is still 3. And this is going to be 2. So 3 equals 2 times the resistance. My resistance is 1.5 ohms. So it has a much bigger resistance because it's taking away the same amount of energy, but there's less electrons going through it in the first place, which means that to take away the same amount of energy as this one, but there's less electrons going through, it must be a more resistive material. Okay, so how you actually would have this, so this is just the basics, how you actually would have this in sort of an exam question is that you would have something like this. You'd have a circuit like this. So this would be 10 volts. You would have here, and you would say that this was 2 amps and this was 3 ohms. You would have something like this, okay? So you know that, I'm not going to do 3 amps, I'm going to change it up a bit. Your 2 amps is going through the circuit, so always 2 amps worth of current. And I know I lose 6 volts of potential difference across here, so if I put a voltmeter here, that would read 6 because it comes in at 10, leaves at 4. This one I'm going to lose 4 volts because it's going to come in at 4. The energy that's left is 4. It's going to leave at 0. It's going to come back and gain some more energy. Okay, you can work out the resistance on each of these resistors. So why don't you have a go? You know how much voltage it has on it, how much potential difference it has lost, and you know the current. What are the resistance of resistor 1 and resistor 2? Okay, so I'm going to use V equals IR. So 6 equals 2 times R. So R1, so it's 6 volts on this one and 2. So that's going to be 6 divided by 2. So it's going to be 3 ohms. So this one must be 3 ohms. What about this one? I know there's 4 volts on it. I know there's 2 amps times by R2. 4 divided by 2, R2 is going to be 2 ohms. Makes sense. Less energy is lost over it, which means it must have a lower resistance. I'm going to talk a little bit about these things a bit later when we talk about Kirchhoff's law, but this is just the basics of using Ohm's law there.